Good afternoon, class. In today's video, what I'd like to do is to go over the next problem in the series of electric field problems. In this case, I'm going to do the trivial case where Q1 equals Q2. So I wanted to point that out because in the last video, I know I did one where Q1 was not equal to Q2. So that's where everything went kind of, not haywire, but the math got really intense. So what I wanted to do was take a break from that for this video and say, okay, what would happen if the charges were equal? So as we saw from the last video, we know what R1 and R2 are. We know we've seen this diagram in the past. The only thing I really changed was that this is actually going to be number 1 on the, this is going to be number 1 in the homework set. So where Q1 is 1, Q2 is now 1, R is 1, and our K is 8.99 times 10 to the 9th Newton meter squared per coulomb squared. So when we look at this, we would say, okay, everything looks about the same, so the math should be just as intense and just as terrible, right? The answer is actually no. It's not going to be that bad, and here's why. Because a lot of things start dropping out. A lot of terms get canceled, which is wonderful, especially for, people who like math. Like when you can see terms just get canceled out, it's so nice. So here we go, and hopefully you'll understand this as well, as you'll see this as well as we go through more of these examples. So we're starting again with the sum of all the electric fields is 0. That's where the electric field will be 0. So we're going to add up our electric fields for charge 1 and charge 2. So KQ1 over R1 squared plus KQ2 over R2 squared equals 0. Again, we said that to the right is going to be positive, and R2 is going to be R minus R1, but we're adding that Q1 is equal to Q2 in this case. So we did all the same work pretty much, and hopefully if you notice that pretty much all the work is the same so far. The difference is that when you get to this step, right, you got Q1 times R minus R1 quantity squared equals Q2 R1 squared, right? We got to this line. Notice that I canceled Q1 and Q2 because they're equal. And of course, there is an exception to this. Obviously, if the charges are 0, then you can't do this because, 0 divided by 0 is undefined. So that you have to watch out for. But other than that, but of course, if you had 0 charge, you wouldn't have an electric field. So that would kind of be a moot point when it comes to an electric field problem. So don't worry about. That's why in this case you can assume that Q1 and Q2 are not 0. So when we divide them out, they cancel. So what I've got is R squared minus 2R R1 plus R1 squared equals R1 squared. So when I have this, I'd say, oh wait, I've got R1 squared on the right side, I've got R1 squared on the left side. I can subtract the two. And that's great. I would love to do that to make this simpler. So then what I have is now R squared minus 2R R1 equals 0. So I say, okay, now that I've got that, well, actually, this looks like an algebra problem. I can isolate R1, the thing that I actually want to solve for, which is in a question mark. So let's do that. And we're doing this in general, so this is great. So here we go. To isolate the variable, I have to do the opposite operation to what's being done to it right now. Right now, my priority is it's being subtracted from R squared. So I'm going to add 2R R1 to both sides of the equation, and then I'm going to say, well, now R1 is being multiplied by 2R, so I'm going to do the opposite operation, of multiplication, which is division, and I'm going to divide both sides of the equation by 2R. So now I've got R squared over 2R, and as you may remember from the laws of exponents, if you've got the same base and different, and the bases are the same, and you're dividing, you take the exponents and you subtract them. So 2 minus 1 is 1. So you've got R1 will equal R over 2. So of course, if you'd be asking, okay, well, now that we're doing that, what about our example problem in number 1? What would the answer be? Well, R is 1, so you replace 1 over here. So R1 is equal to half a meter. So 1 over 2 meters. And that would be the answer to that. So it's, this is, and hopefully you may have noticed, this is actually looks like a really nice, easy way of solving this. And even for a generalized case, this is pretty nice. Because what if R was like 2 or something? then the answer would be 2 over 2, 1 meter. Now you have the formula for how to solve when Q1 and Q2 are the same. So hopefully this general result gets you kind of excited, like, oh, I can actually solve for things. Anytime I see something that is the same, it'll help me out, especially when it comes to tests, because you don't have as much time to really sit down and ponder what type of problem this is. You just kind of need to go for it and know what to do. So if you can recognize this, it'll make things go a whole lot smoother. So with that, that's the generalized case of how to solve for when Q1 and Q2 are the same. Also, it's the solution to number 1 on the electric field problems. Next time I'll work on another one where I'm going to use completing the square to actually solve this, to give you a second method of how to solve when Q1 and Q2 are not the same. So good luck in your studies. May the force be with you.